Welcome back to OCR MEI Further Mathematics B. Today we're doing Chapter 1.1, Simple Proofs. Proofs are important because it's used in a lot of scientific research and also mathematical theory research. In this video we're going to talk about deduction, counterexample, and exhaustion as three main ways of proving a theory. An example of deduction is shown as follows. Show that x squared minus 8x plus 17 is greater than 0. So first of all, when you see an inequality sign, especially when it comes to being greater than 0, we can always do one thing that's really useful, which is completing the square. Because all squares are positive by definition, we can find out if this can become a positive square at a positive number. If that's the case, then it will always be larger than 0. So let's get started. To complete the square, you take half of the value of the x term, which gives us minus 4. So we've got x minus 4 all squared, and that minus 4 yields us a plus 16, so we take away 16 to make this x squared minus 8x. Then we add the 17 and complete the equality, or inequality rather. With that, we can cancel out the 16 to gain x take 4 all squared plus 1 is larger than or larger than 0. So in this step, you will have to actually state, since a square is always greater than 0, a squared plus 1 is, this is actually always greater than or equal to 0, because if x is 4, then you get 0, and this has to be a equality in a sense, but that doesn't impact the result because we're adding 1. It's always greater than 0. And to finish off, you just write QED. So that's the first example that I'm going to do, and next up we have a counterexample example. Second example, disprove all integers that have 3 as a unit are prime. So in this sense, we can take a counterexample, because if you count far enough, there will definitely be a number with a 3 on its end not being prime. So let's get this started. So let's first list every single number from the smallest one up. So let's have 3, because 3 is a single unit integer. Then we have 13, which is another digit 3 unit. Then up 1, 23, and note that they're all prime, which is all fine. So these are all prime, but the next one, 33, is not. So with that said, because 33 is equal to 11 times 3, and therefore disproved. So finally, we have proof by exhaustion, which is often seen as the less brain intensive kind of proof, except that it is actually very useful in certain ways and sense. To prove that n squared plus 1 is indivisible by 4 for n values between 0 and 5, there are only 6 different things that you can do, and so why don't you just try, because it's kind of easy to do so. So start with 0, n to the 0 is 1 plus 1 is 2, so I've got the first value. For n is 1, we have 1 to the square, never mind, it's actually n to the square, which means that 0 squared is 0 plus 1 is just 1. That's the first value. N is 1, 1 squared plus 1 gives us 2. 2 squared is 4 plus 1 is 5. 3 squared plus 1 is 10. 4 squared plus 1 is 17. And finally 5 squared plus 1 is 26. And if you do division by 4 for all of them, you get remainder 1, 2, 1, 2, 1, and 2 as remainders. So this means that for all of these n values, it is indeed n squared plus 1 is indeed indivisible by 4. This cannot be proven in any other way from induction or deduction or counterexample. You can't find, well, counterexample is a special one in this case because you have all the examples. So basically you couldn't actually find a counterexample in this sense. But deduction and induction will not work for this proof, which means that exhaustion is your only bet. And so when you have the last resort to exhaustion, it might be actually the way that you should do, and don't feel like you're kind of chickening out for whatever reason. So when we talk about proofs, it really comes down to experience, and the more proofs you've seen, the easier it gets. One thing that is very useful to note is that when you see an inequality sign greater than or less than, it often means that you want to complete the square. Or if you have a tiny data set which might be less than 10 data point values, or for 10 n values, then you can try to go for exhaustion. It's less brain intensive, you can just grind through them, which will be very helpful. But if it's a very general set, say if the requirement is for a set of data within the real number or a real integer, then because integer goes up infinitely, so you couldn't actually prove by exhaustion that way. So pick and choose a optimum way of attempting your proofs is a very useful skill to have. So it's time for you to attempt these questions. Question 1, prove if C divides A and if C divides B at the same time, then C divides A plus B. Question 2, disprove that 2 to the power n take 1 is prime for all real integer n. Question 3, prove that n plus 1 all squared is always greater than or equal to 3 to the power n for n is between 0 to 2 inclusive. Since these are all proofs and disproofs, that means that there aren't actually an answer to these questions, and therefore this will be the end of the video. If you have any questions, feel free to leave a comment below, and I will see you on my next one.